Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. Last time I gave you 4 different definitions of consistency of a system or of a set of sentences. This time I'm going to show you that 3 of them are equivalent to each other, and therefore it doesn't matter which one we use. We can use whichever one works best for our particular application. This is the case in the context that we are working in, which is classical propositional modal logic. So where we have the principle of non-contradiction and the law of excluded middle. If you drop these assumptions and you start doing non-classical systems, these notions of consistency do come apart. The fourth notion of consistency is also equivalent to the other 3 that we have on the assumption that a particular rule, one that we will have in the systems we'll look at going forward, actually holds. I'll say a bit more about this at the end. That notion of consistency isn't going to be one that we use very frequently. So the main result is going to be showing that S consistency, so consistency with respect to a particular system S, absolute consistency, and negation consistency are all, in the context that we are working in, equivalent. So let me get my whiteboard up so we can show how this goes. We've got first that the notion of a particular system, we're going to look just at systems rather than subsets of that system. So S consistent is going to be equivalent to saying that S is absolutely consistent. And this is going to be equivalent to S being negation consistent. So what we need to do is we need to show that from any one of these, you can derive any of the others. So what we've got is we've got kind of one notion of consistency, S consistency, another one, which is absolute consistency, and a third one, which is negation consistency. So we'll show how each one of these notions implies one of the others so that you end up getting a great big circular implication. So first, I'm going to show that S consistency implies negation consistency. So what we'll do is we will suppose that the system we are looking at, S, is S consistent. And what you remember is that this means that there is no finite set of formulas gamma consisting in phi 0 all the way up to phi n, which is a subset of the system. So, some subset of the theorems that it proves, where the system can prove the negation of the conjunction of all of them. So that is just a restatement of what it means to be S consistent. Now we are going to suppose that it is actually negation inconsistent. And we will derive a contradiction from this. So if it is negation inconsistent, then we know that there is some well-formed formula psi such that within S, you can prove both psi and, oops, sorry, that should have been an S subscript, not a psi subscript. You can prove both psi and the negation of psi. However, it follows that if you can prove both of the formulas individually, that you can prove the conjunction of them. So in psi, you can also prove in S, you can prove both the conjunction psi and not psi. However, because S is built on propositional logic, it is also the case that it can prove every substitution instance of every propositional tautology, including this one. But psi and not psi were both theorems of S, so they are within S, and we can prove not the conjunction of both of them. So in fact, this means that if it is negation inconsistent, it is also S inconsistent. So that gives us an implication from S consistency to negation consistency. Now I'm going to show that absolute consistency implies S consistency. So if you've got a system S, which is absolutely consistent, which means that there is at least one formula that it doesn't prove. So there is some well-formed formula psi such that in S, you cannot prove psi. Now we're going to suppose that, in fact, this system is S inconsistent. So suppose S is S inconsistent, and we'll use this to derive a contradiction. If it is S inconsistent, then we know that there is a finite set gamma, which has, again, some collection of formulas, phi 0 up to phi n. These are all going to be some subset of the overall system. And in S, you can prove the negation of the conjunction of all of them. This is just what the definition of S inconsistency says. However, since gamma is a subset of S, we also have that S can prove the conjunction of all of the formulas. But then it means that we can prove this conjunction and the negation of exactly the same conjunction because we are only looking at classical systems that validate the principle of non-contradiction. What this means is that if we have both of these in our system, we can then derive through propositional tautological reasoning that if we have the conjunction of phi 1 to phi n and not that same conjunction, this together implies any formula whatsoever, including psi. So then by modus ponens, again, propositional logic reasoning, we have that within S, you can prove psi, but we had assumed that S was absolutely consistent and that psi was the formula that it couldn't prove. So this shows us that if we have something that is absolutely consistent, we have something that is S consistent. Now, because these are implications, if 2 implies 1 and 1 implies 3, we know that 2 implies 3. So all we need to do is to get one inference that goes kind of the other way around the circle, and we will have shown that these are all equivalent. So the final one that we're going to do is we are going to show that 3, negation consistency, implies 2, that is absolute consistency. So if S is negation consistent, then for every well-formed formula, phi, either you can't prove phi or you can't prove not phi. But this means that absolute consistency falls out of this almost by definition, because it says that there's at least one formula that you can't prove. Here, negation consistency says actually for any pair of formula plus negation, at least one of them is not provable. So it's like loads and loads of things that you aren't able to prove. So this means that negation consistency implies absolute consistency, but that implies, and now we've got our complete circle where everything implies everything else. Just a note about atomic consistency. Atomic consistency says that there's at least one atom that you are not able to prove. Now, atomic consistency clearly implies absolute consistency, because if you can't apply some atom, then if you can't derive some atom, then there's at least one formula that you can't derive. Now, how about the other way around? Suppose that you have something that is absolutely consistent. That means there's at least some formula, but it might not be an atom. However, then assume you've got a system that is atomically inconsistent, i.e. you can prove every single atom. Actually, all you need is that you can prove one, and this result will go through. If you have a system that validates uniform substitution, and this is a rule that we'll be talking about in just a couple of videos and is something that all of our modal systems do validate, then if you are able to prove an atom, you are able to prove any substitution instance of it, including the formula that you assumed you couldn't prove because you had an absolute consistent set. So that shows that this fourth notion of consistency is equivalent to the second one, and therefore equivalent to all of the others as well. So there you have it. This goes to show that it doesn't matter which of these notions of consistency we use in any given context. Most of the time, we will just use the notion of S-consistency, that there's no finite subset of the set in question where you can prove the negation of the conjunction of all of the elements of the set. But the other definitions are useful, and you come across them in the literature, so it's worth knowing that ultimately, in our context, they all mean the same thing. This lays all of the foundation for actually defining particular proof theories. So we are going to start that next time. I'm going to give you System K, the basic classical propositional modal logic system. Join me then. It's bound to be fun. Take care and see you later.